Okay, so good lunch that they are not saying anything. So I specifically asked the security to not to switch on the AC, otherwise we will be dozing off. Okay then, I hope the poster sessions were helpful for everybody. So anybody landed job like no? Okay, if you land a job, 10% commission is mine by the way. Okay, fine. Without further delay, let's welcome Devasri for the next talk. Dr. Devasri Tripathi is an assistant professor in computer science and engineering at IIT Bhubaneswar. Her research spans in computer architecture, machine learning, hardware software co-design of AI systems, energy efficient computing, sustainable AI, tiny ML, and systems for healthcare, drones, autonomous cars, and robotics, mobile and edge computing. Her current research focuses on ML for systems and systems for ML. Prior to joining IIT Bhubaneswar, Dr. Tripathi was a postdoctoral fellow in computer science at Harvard University in Harvard Architecture, Circuits and Compilers Group. She is currently working as an associate with Harvard University. She graduated from University of California, Riverside with PhD in computer science. Over to you, Devasri.
Thank you so much, Sumit. Welcome to the talk. And I know, the post-lunch session is the most difficult one. So the speaker is trying to sleep. The audience are trying to sleep. So I'll try to not take too much time and get started right away. Feel free to stop me anytime during the presentation as you see fit. So I'll be talking mostly about the energy efficiency aspect of running large language models on the GPUs, the accelerators. So let's start by looking at how has the deep learning hardware evolved over the years. So there were some of the talks that focused on the microarchitecture, especially the memory system optimization. There were some of the talks who took help of AI from the security point of view, and so on. So it's basically the other way around. How has the computer architecture or the hardware platform evolution helped in bumping up the performance or the throughput of the deep learning systems? So if we take a look at the figure where on the x-axis we have the years and on the y-axis we have peta, the floating point operations per second, multiplied by days in training. So we see that the initial 2 points were AlexNet and ResNet, and something happened during the 2017-2018 time era, after which we saw a big jump in the in training performance from BERT, GPT-2, Megatron, and so on. So what exactly happened in this timeline? Any guesses? So anyone of you have heard about the paper "All You Need Is Attention"? So when did it come? 2017, and that was one of the breakthrough in, it introduced the transformer models, and after that the models started scaling like anything. Then is the next figure, which talks about the GPU inference performance, which has increased more than 2x per year. So we start with, again, on the x-axis the years, and the names here basically show the generation of the GPU, Kepler, Maxwell, Pascal, Volta, Turing, and Ampere, and then what is exact model which gives the specific inference performance in terms of int8 tera operations per second. So from K20 to M40, we don't see much of a speed up, but from M40 to Pascal, we see almost 3x speed up. So what exactly contributed to that speed up? The answer is here, because of the introduction of the NVLink, which aided in the GPU to GPU communication measured over the floating point 32 data types. Then again there was this huge jump from 21 to 125 from Pascal to Volta. That happened because of the introduction of the NV switch, which aided in the high performance networks connecting where the GPUs were connected using the InfiniBand, and they also introduced the tensor core architectures, the flexibility for programmable architecture. So why is InfiniBand or NV switch that important? Any thoughts? So why were we discussing this, or why is it worth a discussion? Attention. Yes, we are coming to that. But so basically all the deep learning models or training, whatever happens in the data centers have hundreds of GPUs connected to each other through some interconnection network, InfiniBand, and the communication takes a lot of time. So if you are able to cut down on the communication time by having a advanced hardware improvement, then you are actually saving a lot in terms of the overall training time or the overall inference time. That's why the role here is important. Next is again a 2x jump from Volta to Turing because of the introduction of the integer tensor cores supporting INT8 data types. So you can fit in more and more different types of data types in the same space, so you can save on the resource utilization part. And then there was a jump from 261 to 1248 from Turing to Ampere, and one of the major major contributing factor to this was the tensor core support for sparse data computation. So now coming on to, okay, we know that like there has been a lot of improvement in the GPU hardware which aided in scaling up the deep learning inference performance, but what is the cost of it? So here I am analyzing again the same generation of the GPUs, Fermi to Blackwell. So, and the year in which they were launched is mentioned here, and the semiconductor node on which they were built is mentioned in the brackets. So as we can see, from 2010 Fermi to Kepler to Maxwell to finally 2024 Blackwell, the blue bars are the bars that make us happy, that basically represents the performance in tera floating point operations per second. We can see that they are able to deliver good performance or good throughput, but at the cost of the orange line, which is the thermal density power, thermal design power, that also increases at the same rate. So what is the reason for this? Why is the orange line increasing at such a massive rate? Any thoughts? So yes, there are microarchitectural changes. We are fitting in more number of cores. There is also the technology scaling that is playing an important role in this. And because of the technology scaling, the thermal design power, the static power is becoming increasingly more predominant compared to the dynamic power. So we need to take care, or we need to introduce better power management techniques to make sure that we are able to scale it up, because if you are having a thermal throttling, if you are running some gaming GPUs and so on, and you are using the maximum performance or your throttle, then you will see that the frequency goes down, because with frequency your temperature increases, and that's not a scalable solution, so your frequency will automatically go down, right? So that's when you are reaching or hitting the thermal wall problem. So we need to care, if we want the same thing to scale up, if you want our next generation of GPUs to meet the same performance demand that are needed by the deep learning models, then we need to think something about the power management techniques.
Sorry, so you said that much of the increase is due to the static power?
So if we see the static power increase and the dynamic power increase, we see that earlier in 2010 the static power was much less than the dynamic power. They have now almost touching each other kind of thing. Dynamic power, if I don't use the same component, if the activity factor is less, then dynamic power is in control.
Yes.
But I can't do much about the static power as long as the system is.
The fact that the static power is dominating is well known, but yeah, the increase is, but the static power itself has not increased over the years, right? Oh, sorry.
But it has.
Professor, you have to multiply that with the number of transistors.
Yeah.
And that is going exponentially.
Yeah. With the technology scaling. So, so the takeaway of this slide is, with the increase in the GPU performance demand, our power consumed by the GPUs is also increasing at an alarming rate. So, and then like all of us are well aware of the power wall problem, because if you keep increasing the power at the same rate, the circuits will become unsustainable, reliability issues will occur, because of the high temperature will end up with faulty circuits, it's expensive, not environment friendly. So to shed a little bit of light on this, you remember like 2017 to 2018 time era when the Bitcoin mining was really getting the momentum. Everyone wanted to try their luck, wanted to get rich by doing the Bitcoin mining. Many of the GPUs from the market were gone, taken by the Bitcoin miners, and then like the climate change problem become a serious problem because the power which is dissipated by the GPUs is dissipated in terms of heat, which is leading to the climate change problems. So the large language models, companies also saw that as one of the things. So that's the reason they also have this alternative as small language models, which lesser number of parameters. So the advantage of this is like, of course, it's accessible and affordable. You can run it on the small local GPUs. It's much more energy efficient, and it's more accessible, cheaper to develop, customize, etc., etc. So now coming to the topic, so Gen AI is actually getting a lot of attention, and so the paper, All You Need Is Attention by the Google Brain Group in NIPS 2017, it introduces the transformer architecture. So many of you might have seen this figure over and over again. So it has an encoder component, decoder component, and so on. And with that, we see a lot of companies in the AI race have launched their own LLM models, and now we are in a race to like go till the artificial general intelligence. So what is artificial general intelligence? It's basically a theoretical concept which we are trying to reach, where we are hoping that the AI or the Gen AI models are going to show human-like intelligence with the ability to self-teach itself. Okay, so now coming to the concerning part. So all this improvement or development is having at the cost of lot of energy and carbon emission. So let's think of the AI chatbot, which is basically trending, a hot application that we keep using for assignments, for question designing, for whatnot, right? So let's be fair, like both the instructors and the students are using the chatbots to their to meet their needs. And so these chatbots are actually trained on the data center, which has 100,000 GPUs. And what happens is that, like, if we see, like, this is a statistical data, so the GPU shipped by NVIDIA can use up to 14.4 terawatt per hour power in a year. So it's very energy hungry, and it eventually translates to 3.7% of the total global greenhouse gas emissions. So can we do anything to reduce the power and energy used in the large language models? That's the question that we're going to answer in the subsequent slides. So little bit of overview of the things that I have touched on in during my PhD and thereafter. So there are some well-known traditional power management techniques. So one of them is DVFS, dynamic voltage frequency scaling. Some of the colleagues sitting in the audience have used extensive DVFS in terms of the memory subsystem energy or power management, and also the undervolting. So undervolting as in, so the manufacturer specifies a specific minimum and maximum voltage range for operating any device, right? Don't go below this, don't exceed beyond this voltage. But what we did, we also explored what happens if you go below that minimum voltage operation, and can you save some power or not. So that's one of the topics that we also touched upon. And second thing is overclocking. Overclocking means if you are going like voltage minimum and voltage maximum, we also have frequency minimum and frequency maximum operating range. So what will happen if you exceed the maximum frequency? So if you are exceeding the maximum frequency, what happens is that your execution time may likely reduce. So if your execution time reduces, for the rest amount of time you can switch off the circuit or power gate and save on your static energy. So that's one of the commonly used power management techniques as well. So now the question that we'll try answering is how are we going to minimize the power usage of the AI, for example, in different parts for training, fine-tuning, inference. And the next important question is what is the more energy hungry phase? Is it the computation? Is it the communication? Which one of these is that? So it needs a lot of workload characterization to understand the behavior of the application, to see which is my bottleneck in terms of the power consumption, and then we can apply different techniques based on our findings. So let's take a look at the LLM training, a bird's eye view. So here we have taken the so this is not my work, this is from my PhD research group. This is the base paper that I'm building my work on, so that's the reason I put it here. So it was published in IISc 2024. So they have taken a microllama benchmark for training, and then they have for the profiling, from the profiling they see that there is a forward pass, backward pass, and parameter synchronization. So the forward and backward pass involves computation in the GPUs, and in the parameter synchronization, it's basically all reduced kind of communication happening between multiple GPUs involved in the training process. So to see what is the most time consuming process in the overall training time, so they have three legend. In the legend they have three categories: idle time, compute time, and communication time, with the communication time shown in blue. So we see that for the microllama application, it's very significant, and also it's like we can think of it like consumes 30% of the time on an average, taken all the application together. So communication does take a lot of execution time. So what do we do about it? So so the takeaway is mentioned before. Now we will see another important or interesting characteristics of the microllama application training. So here we have broken down the time in computation phase, communication phase, and so on. So in every epoch, so we have computation and communication involved. And on the primary y-axis we have power, and on the secondary y-axis we have frequency. The frequency is shown in red and the power is shown in the blue. So one peculiar observation that we saw was that and the maximum and minimum frequency operating is shown as the bounds of this figure. So the observation was that during the computation phase, the red line is actually dipping down, and during the communication phase, it's actually shooting up. So the frequency is increasing during the communication phase, and it's going down during the computation phase, which is really counterintuitive, because in computation you are actually using the course, so it makes more sense for you that like during computation you have better frequency, and during communication probably one SM or one GPU is participating in dividing the data among the different other GPUs. So this observation is really counterintuitive. So probable reason that we could think of is maybe thermal throttling, where the GPU is actually tuning down the frequency when the extensive computing phase is increasing the temperature of the GPU, and that's the reason like during the computation phase we are having lesser frequency. And another guess is basically we see that that's the reason for the high frequency during the communication phase, which is clearly unnecessary. So the next goal which they had was to increase the yes.
The communication phase is essentially updating the parameters, or is it
parameter synchronization?
Synchronization,
Yeah.
that's essentially what we're talking about. So this is more like updating the memory rather than communication between the GPUs, right? Or is it more like communication from the GPUs to the memory?
So communication between the GPUs.
Between the
GPUs, like all reduce operations, scatter gather operations. So basically whatever the NCCL library, NVIDIA Collective Communication Library operations, so those are the ones being called in. Okay, so going back to this, so the next intuitive step, as we can guess, is what will happen if I reduce the frequency forcibly by capping the power, like do not go beyond this power, so automatically the frequency is going to go down. And how is it going to impact my final execution time? So that's what they did. So using the APIs and NVML library APIs, they try to bring down the frequency during the communication phase. And the observation was that, yes, they are able to save a good amount of energy, which is about 17.3%, So the optimization that they did in the communication library, they named it as PCCL, and the baseline was NCCL, which is the default NVIDIA the collective communication library. And the impact on the training time, the overhead was about 1 to 2% higher than the NCCL. So that was one of the work that I wanted to talk about. How much time do I have?
Maybe 7 minutes.
Okay. Then I'll quickly go through the LLM computation without going through the algorithm aspect, just zeroing down into what exact component I'm interested in. So the transformer, which is again introduced in that 2017 paper, basically serves as the backbone of the large language models. So here we are seeing the example of a language translation where we are translating from one language to another, and it's a sequence to sequence model where yeah, so here what happens is that each token is taken by the encoder. Encoder generates the context, and what the decoder is actually processing and filling in, giving the output token by token. So next is we know that like the heart of the transformer lies in the attention mechanism. And what is attention? I'll skip all of this. So we'll try to understand attention using this single line. So the sentence that is given to us is the animal did not cross the street because it was too tired. Now the question is, the it pronoun refers to the animal or does it refer to the street? Which word is it referring to? So using the encoder decoder architecture, we try to find the weights, and we see that the one having the thickest line or the highest weight line is the animal. So the conclusion that it will draw is it is referring to the animal, not to the street, right? It's a simple algorithm. Now what lies or what mathematical operations actually happen during the self-attention network is a bunch of matrix multiplication. So we have different embedding vector, and we are supposed to calculate the query, key and value vector using some matrix multiplication operation. So now let's go for, we know that matrix multiplication is a very commonly occurring operation in transformers. So applying Amdahl's law, we'll try to make the common case efficient, or we'll try to find out what is the efficient way of doing matrix multiplication on GPUs and what's the most energy efficient way to that. So we did some of experiments for matrix multiplication on the GPUs. So what happens is that we have the like supply voltage, operating voltage, and about 20% of that voltage is accounted for the guard band. So the guard band starts like from the V minimum below. So what will happen if you go below the V minimum also, your GPU is not going to throw errors. It will still work. That is because we have accounted for guard band while designing of this GPUs, and it constitutes almost 20%. So if you leverage this 20% guard band and reduce the voltage of the GPUs, you will be able to save 25% of the energy, because straight away you are saving on the static power or static energy of the GPUs. So we use the same idea, and we went below the undervolting. By the undervolting, we reduce the voltage of the GPUs, and which means the execution time increases, yes, but the overall power decreases. So we saw that we were able to save good amount of static energy by reducing the voltage. When we reduced the voltage, we had faults because there were bit flips and it gave us wrong results. We tried to correct those on the fly using some fault tolerance techniques, algorithm based fault tolerance techniques, and overall we were able to save some good amount of energy and power. So the main takeaway is like we found an analytical model where we changed the matrix sizes of the matrix multiplication application. We changed the different voltage levels by undervolting percentage, and we also saw how many faults you are going to have. Because like even if you use ABFT, but there is a limit on how many faults at a given point of time your fault tolerance techniques can tolerate or correct. So we developed this analytical model, and based on that we were able to save some good amount of power. So I'm trying to extend the same idea in the context of LLM. So that's my current ongoing research work that I'm focusing on. And my research interests are in GPU, where I do runtime management for power and scheduling, performance modeling, compiler assisted techniques with the thrust areas of increasing the performance, energy efficiency. Other side of the research interest which I did not discuss was SOC design for the automated design space exploration. So thanks Pravad sir for giving me some insights into that. I'm excited to try it out, and I'm happy to take any questions that you might have.
Questions?
So the last part you said, what is the increase in the execution time by reducing the energy?
What is the increase in the execution time? So you are asking about the trade-off that we got.
Correct.
So that was about 5% increase in the execution time, but the energy that we reduced was like way more. So I don't exactly remember the numbers, but it was significant.
Okay, more questions? We have time for questions. So one question from me, or rather one comment. So we're showing that that communication time is more, right? So it may be because you are using all reduce. It's all-to-all communications like broadcast. So I think that's why the communication time is more. So there is another scheme called ring all reduce. I think that is also implemented in NCCL, but it's not used because the overhead is high. But in ring all reduce, the communication time is less than all reduce. Like it is.
Okay, so that specific figure, they had tried all those APIs, I think 7 or 8 APIs, like scatter, gather, many other APIs were used. Probably that's why they are getting a higher communication, and also this does not have NVLink. It has PCI bus, which is slower. So that's one of the potential reasons, but the counterintuitive part is the frequency part which I'm chasing. I'm trying to find an answer to that.
Okay, got it.
Thank you.
Question? Any more question? Okay, if there is no question, we can thank the rest. And a small memento.
Thank you.
Of current generation of AMD Ryzen or EPIC processors. Over to you, Devi.
Yeah, thank you, Sumit, and thanks for inviting me for this talk. I hope I'm audible. I'm in a lot of performance talk, lot of graphs. I'm not going to show you my graphs. That's for later. I'm going to, as my talk suggests, it's more about opportunities, right? So where we can exploit the opportunities, and I'm going to discuss about the various designs those are possible in the 3D stack environment, right? So now, obviously, I'll start with a story. So this is my story. So previously there were few people, right? The population is growing, right? And we were building houses and individual houses. We had a lot of space, we were building individual houses and so on. But then when population started increasing, now we are going for apartments, right? So the same technology has been translated into the chip design also. So previously there was a lot of space. They were using the chip area to design multiple cores, keeping the caches and so on. But now with increase in caches, demand of more and more data, so the chip space is reducing, so we are going for 3D stacking. So now how do we do 3D stacking, and what is exactly a 3D stacking technology? So in the traditional approach, increasing die size and shrinking the logic worked, we were able to generate a lot of space on the chip, and we were able to push in more and more transistors, bump up the logic, and get more and more performance. But obviously, we are going towards the 2 nanometer technology, right? We are almost saturating the chip, and we literally have no space. So even if in company, if you say that I have come up with an optimization of L1 cache, which requires 1 bit per block, they should get out. Please get out. We cannot do that. We don't have space. Simple. So what do we do? So the newer technology which is coming up is the 3D stacking technology, and this I'm going to mostly talk about the SRAM based 3D stacking technology. I'm not going to go into the DRAM based 3D stacking technology, which you might have heard previously regarding the DRAM caches and so on. But now we are going to discuss about the SRAM based 3D stacking technology, which uses the through silicon vias to connect those under base layer into a stack layer. Now this has, the process technology has enhanced very fast, and we really have now a real chip which has a 3D cache. So the AMD V cache is one of the first processors to have the 3D stacking caches. So they are the last level cache. They are large caches stacked on the last level cache. So basically, this is your base layer, and there are through silicon vias which are connected here, and then there are these caches which are stacked upon the 3D stack layer. So now, what are the products which are typically using the 3D stack cache? This is mostly called as AMD's V cache, and this AMD's V cache has got a 64 MB of SRAM cache over a complex of 8 cores, which they call it as CCD, core complex die. They have a core complex die of 8 cores which are connected over an interconnection network, and there is a base layer of SRAM which has got 32 MB in the L3 cache. So particularly 4 MB per slice. So it's a distributed cache architecture, and it has got 32 MB per slice, and then you stack 64 MB of data or cache onto the base layer. Now when it goes to the server, this multiplies actually. This for a 64 core, it goes up to like 512 MB of stacking and 256 MB on the base layer and so on. And some of the servers are kind of named here. Recently, with the 8000 series of processor being announced, they are saying that even the mobile laptops will have a 3D cache in their chips, right? And having said that, it's not that just AMD is doing that. Intel tried doing a large DRAM cache long back in 2015, which is used in this King's Knight's Landing chip around the timeline of 2015. Okay, so now I did say that I will not show a lot of graphs, but this is the only graph I have. So what is happening here? This is basically a comparison of the 3D cache versus the non-3D cache system, and if you see here, the performance gains are huge. Just with the CPU, we don't expect such huge gains in terms of performance in case of CPU optimizations, but using a large cache is helping in several applications to reach around 3x performance, 1.8x performance, and so on. But if you see the names of these benchmarks, they are not old benchmarks. They are not the classical spec benchmarks. They are more of like DNN, 1 DNN, open foam, and so on. So mostly the latest vision-based applications that you can think of. So those are the things which are getting more and more performance and so on. So if you see here, several applications are getting more performance, and they are not in small range, 20%, 30%, and so on. And by the way, these are real data. These are not simulation data. These are collected from real systems. Okay? And that's not the only thing. There is something performance drop also. We expect that increasing the size of the cache, we'll always get performance, right? But that's not happening. Even increasing the size of the cache, we are losing a lot for various applications, and that too in not small numbers, 6%, 5%, 6%, and so on. This is a small list. This is a huge list. If you want to go to this website, you can see the complete list of benchmarks that they're published, where there is a significant drop in several applications and significant increase in several applications. So it's a trade-off. Basically, you don't know which particular application is going to benefit, which won't. Now, I hope you might have heard this. AMD is trying to sell these processors with the name of gaming PCs. Why? Because simple reason is they benefit a lot with the graphics application and gaming benchmark suits. Okay, so now we see that the drop in performance is maximum of 6.2 over a non-stack version, and this drop in performance is mostly, as reported and as of I analyzed, is mostly because of this 4-cycle latency of L3 hit. So although you get an L3 hit, you still have a 4-cycle latencies to access the data. Okay, so in such cases some conflicts happen. That is one of the reason. But the major reason is that because it's 3D stack, there are thermal challenges. So because of these thermal challenges, the frequency of the system has to be tuned down. So a baseline processor will have a higher frequency than a 3D stack version of a cache, which will have a lower frequency. So in final, your IPC might be growing, but because of the frequency factor, the overall performance is, the runtime is going to reduce and the overall performance is going to drop. So with that, okay, I have another slides for people who are more interested towards vision benchmarks. There are even more performance gains like 15%, 13%, 30% and so on. So with this motivation, I'm going to discuss about the different kind of opportunities that we have that we can explore in the case of 3D caches. So now going back to the basics, so we have the tile chip multiprocessor. I think I need not explain this further because already John has given a very in-depth description of these things. So I'll not go into these details, but the thing that I want to say here is that it's, let's say it's a 16-core network. You have one of the node and there is a CPU connected to that node with a shared L2 cache and a private L1 cache and so on. So that's what we typically believe that is the CMP. But the actual CMP is basically having two levels of private caches, L1 and L2 cache, and typically the L3 cache is like a shared and a distributed, over the network and so on. Okay, so now this is what we expect, but the actual system is even more different because of the practicality. We may not be able to deploy more than 64 core inside one set of cores, so which we call as complex. So what if we want to scale beyond 64? What do? We have to use networks, network of network. So that's what the current systems are also doing. So this is one of the examples of the Zen 5 architecture of AMD, which has got a core complex of 8 cores connected over a network. So there is a network here and the L3 cache is distributed. These 8 cores are connected over the network and it forms one CCD or core complex die. And such core complex dies are connected, multiple such core complex dies are connected over something called as the infinity fabric, or which is otherwise the cache coherence master of these cores with respect to the IO devices also. Alright. Now bringing back 3D into this, so where the 3D sit here. So basically let's look at the topology. So we had this in the previous slide. We saw that there are 8 cores here and there is this L3 cache sitting over a shared and distributed network in these 8 cores. Now we can make that 2-dimensional interconnection network as a 3-dimensional interconnection network here. So your caches might be a different set of slices which are distributed over this 3D mesh. Typically a hypercube hypercube network can be better in order to communicate between the chiplets. What do you mean by chiplets? So in the previous diagram, if I want to manufacture these as separate units, I will call them as chiplets. Okay? So you have a dedicated set of components and you have another set of dedicated components and you want to connect them to each other. So you manufacture each of them as chiplets and you connect them to each other. Okay? And that connection is going to be via a hypercube network. Alright? So apart from this topology, so this means that rather than just thinking of a mesh 2D topology, now we have to think of algorithms which will work in a 3D topology, 3D mesh topology. Also, we have to take care of the fairness challenges in there because multiple cores will pump in packets from different directions. So let's say, for example, right now you might be having the cores at the bottom layer, but later you will see that the cores will be in the top layer nodes also. So everyone will start pumping. If everyone starts pumping, then there might be fairness challenges inside this network. Then the last part of the topology is the different network channels. What are different network channels? So typically we imagine that there is one set of link in the between the L2 and the L3 cache, and it is transmitting all the different types of packets. Like there is reads, there is writes, there is data. Everything is getting transmitted through the same channel. It may not be necessary. So you need to have multiple different network channels to transmit different types of packets and so on. Alright, so now this will what will be the future. I mean, this is the 2D mesh network that we are talking of, and we will be translating this into a 3D network where multiple nodes are connected to each other, and there are some through silicon vias. So this third dimension will be the through silicon vias, which will be connecting from the base layer to top layer. Like we have in our apartment, we have our lifts, which used to transfer us from the base ground to the top floors and so on. So in this sense, if you talk about routing, there are various routing techniques which have been proposed in a 2D system. For example, there is XY routing, there is north-south routing, or there are several different types of algorithms are present in the 2D network. Now those algorithms needs to be again reiterated in a 3D manner. That means you need to think of XYZ routing. What can cause deadlocks in these kind of things? We need to prove different algorithms to determine what can generate a deadlock. We need to be careful about these kind of transmission. So we need to think of different algorithms for that. Now, as I said earlier, because it's 3D, it might cause higher temperature, and we might need to turn down the frequency. Now, why is that going to happen? So if you see this circuit board, this is the PCB, you can say, and your chip is sitting on the PCB. So what will happen is that the base layers, typically we put the cooler, we put the thermal cooler on the CPU, right? So if you put the thermal cooler on the CPU, then what will happen is that the top floors of your chip is going to be cool, but the heat will start getting dissipated at the, sorry, not dissipated, will get clogged up at the bottom of the die. So what will happen? The lower ones will get more and more heated. So there is a gradient here, that you have a heating core here and you have a very cool core sitting at the top. Core or memory, you can think of whatever. So if it is a 3D cache only, then these will be memory, and later let's say there will be cores attached to these nodes, then these will be cores also. So what can we do to control that? Of course, dropping the frequency is what is being currently used. So they turn down the frequency a little bit such that we don't generate that much amount of heat, and we are in a cool state, but dropping the frequency will what? It will reduce the performance directly. It will impact the performance directly. So what else we can do? We can maybe try off with cache slice switching off. Of course, we might lose performance there also, but we can completely turn off some of the cache slices for certain period of time, assuming that everything going to that might be going to be missed and being serviced from the memory. Similarly, we need to do some kind of intelligent cache data mapping such that we place important data in such resources, such part of the network, such that we will be able to access that more frequently without hitting up the system and so on. In fact, if you think cores in the middle, so if you see it's a 3D structure, right? So some cores in the middle, even those will be heated up very fast. Why? Because it will see the heat from different nodes nearby. So those also will be starting to heat up. Okay. Okay, so now let's come to a 3D based design choices for what can be done with respect to the tag management of the caches and so on to improve the performance and the power management of the system. Because it's a 3D network, where do we place the L3 tags? That is one of the questions, right? So it's a 3D network, so that means that we can place the tag either at the base layer or we can place the tag at any of the nodes associated with any of the points over the network. That means let's assume that this is a network and these are individual nodes and so on. These are individual nodes. Then what you can do is basically store all your tags for the base layer as well as stack layer on the base layer by itself. What will that do? That will accelerate, actually the design will be simpler first of all, and the second thing that will happen is that the misses will be accelerated. Why will the misses be accelerated? The simple reason is the memory controller is sitting in the bottom layer. So if you place the tags at the bottom layer, you can very quickly decide if something is missed, just send it to the memory controller. But whereas if your tags are stored at upper layer, so you have to send your packet to the upper layer and then there you figure out that it's a miss, you come down again and then you go to the network. Okay, sorry, you go to the memory controller. So you will have more latency for the misses if you start storing everything at the stack layer. But the other problem that will also come is that in the base layer is that, sorry, that the first one was an advantage. The disadvantage is that there will be a lot of traffic. Because it's a 3D cache, now there will be a lot of traffic at the base layer. So the traffic optimization, the memory traffic optimization won't be possible. Sorry, the network traffic optimization will be difficult, right? So if this happens, the bandwidth will reduce. Although you try to improve the latency, the bandwidth is going to reduce there.
So if you do the tag checking at the lower layer, and if think of the case, maximum of them are hits.
Correct.
So still there will be traffic that is going up and it's a dual traffic, right? Or you are going to duplicate the request. Tag comparison is one packet, the data taking is another packet. So it's dual basically.
Yes. Once it enters the network, it has to be split up.
Okay. So normally what means you are not saving anything in the traffic, right?
No.
And generally caches, we assume that it's having higher hits. And
Yes.
you are telling you are trying to exploit miss. How do you comment on it?
No, see, the point is that it's not necessary that your application is going to fit into even a large cache, right?
Yeah.
The way the applications are growing, the amount of data required by the application is growing, it's not necessary that it is going to fit in the cache. So you have to think of the miss scenarios also. Otherwise, the complete performance will come down, right? So of course, the once you will get a hit, you might benefit, but for the misses.
But this is not talking about the placing in a different way. Those which are not frequently accessed is kept farther. That way you are not remapping. Right?
We are not. So right now we have this. So this is all in the exploratory phase. So
Yeah.
I mean, all those things are valid ideas. That's what I wanted to say is that whatever the whole design space of cache, whatever has been done in the 2D, again now becomes a new problem. So you have to all rethink in different dimensions. And this is just one example that I want to give. The next slide will just touch upon all the other possible choices. Okay, so now the third choice can be a combination of this, where you use some kind of micro tags, where a part of the tag is placed in the base layer, and based on that you decide that okay, it's a hit or a miss. So filter out the traffic and send a lot of requests to the memory, and rest you send it out for the actual tag comparison. Of course, this is going to be consume more area overhead and so on, but you get the optimality of the latency and the bandwidth there. Okay, so what other things? There are a lot of other design choices that is going to come up. Data placement. Do you place the data in terms of distributing it as a bank, or do you kind of distribute it as different ways? Do you distribute the ways to different stack layer, or they will be different banks? That will determine the overall bandwidth of the L3 cache. Furthermore, there can be cache bypassing and speculation, because some application will never benefit from the L3 cache. Like we saw, we were losing some 5% and so on. So can we exploit some technique by putting something in the base layer and just simply bypassing the L3 cache and going into the memory if we are not getting a benefit from the L3 cache? Similarly, prefetching, multiple prefetching techniques can be explored, because it's a large cache. It's a large cache. If you can do some aggressive prefetching, populate your L3 cache completely with lot of data, then you might hit a good bandwidth. But you might see a good L3 hit bandwidth. But the problem here is that with prefetching is that typically, at least we have seen this, that the moment you start prefetching very aggressively, your memory gets saturated. The memory bottleneck, memory bandwidth gets saturated. And the moment the memory bandwidth gets saturated, your demand access gets delayed. If your demand access starts getting delayed, then the effective performance automatically reduces. Okay, so of course the large space is available, but how do you utilize that large space? By looking into the bandwidth constraint is one of the big challenges. Okay, so now even let's say you prefetch some data, where do you keep it? In which layer you keep it? Do you keep it at the base layer? Do you keep it at the top layer? That will also determine the latency of the data access. So the hotness of the data will be considered, and where do you place the data, that matters a lot. Furthermore, if someone can think of different layers of coherency, that is even more better. I don't want to go into that because that's another complete domain by itself. So where you place the directory, how do you manage the coherence between the layers, if you want to think them as different levels of cache also. Alright, with this I will like to introduce a bit to the chiplet architecture. What does a chiplet architecture, what exactly is a chiplet architecture, and how is it going to scale? That's probably one thing to discuss here. So if you see, chiplets are segmented processors. That means you have different small processors built separately. They are built, they're kind of fabricated, and they're put into a single monolithic chip. They're not a single monolithic chip, but they are fabricated separately and they are put together. Now, with this, what happens? So this is an example of one of the chiplets. So this is specifically the AMD's Zen 5's CPU chiplet, which says that there is a network, and each of the network at the corner node is connected to a CCD. The CCD I discussed earlier, which has 8 cores and a particular node out of that is connected to the network that connects here, and all these nodes are connected to each other using the Infinity Fabric. So this Infinity Fabric is nothing but the coherence manager, and it connects to the GMI link. What is the GMI link? GMI link is your memory link. So basically you can think of it like the IISc interconnection bus and so on. So this GMI link connects to your memory controller and so on. Now it also connects to the PCI and all other devices. Now what is going to happen is that later this network is going to be slowly replaced by the CXL protocol. this new CXL protocol is coming up, which is going to combine different devices, have different devices sitting on the same chip. So you are going to connect these network into the CXL network, and then different devices have to communicate with each other. So it needs to be coherent. The cache coherency has to be taken care of between the different devices and so on. What does this allow? So when we do this kind of chiplet architecture, what it allows is to ensure that we maintain the power aspect of the system. So we are able to control the thermal aspect of the system, so it is easy to dissipate power, because these are small devices, so whatever power is consumed by the small devices and so on, it will just keep transmitting and we can control the frequency very well here. So that is the main agenda of building these kind of chiplets. Now what about chiplets and 3D cache? Sorry.
So maybe it's little off, but the GPU direct link would be compatible.
Yeah, that's a good question. Okay. So this is the fabric, right? So the fabric connects. So it's, you can assume that this is like the North Bridge design. Okay. So you can assume that the GPU will connect to any of these nodes. In fact, the integrated GPUs actually connect to these nodes. So if it is a dedicated GPU, then it will go via this PCI. So the PCI slots are there, right? So it will go via the PCI and connect to the dedicated GPUs. Okay, but integrated GPUs, you can just replace these CCDs with one of the integrated GPU CCD and so on. Okay, so now what can we do as with respect to 3D cache and this chiplet technique is that you can use 3D cache itself as a SoC cache, system on chip cache. That means that in this network itself, one of the node will be a 3D cache. It might be a large cache and it will be shared by all the CCX, right? So the traffic that will be seen by those caches will be different from the traffic that you will see at an L3 cache level. Okay. The other thing that, of course, the interconnect design will be complex because you are putting all the 3D cache together. It becomes a one single unit. The interconnection design will be difficult. But then there can be specific way to control the power. It might be, in fact, easier to control the power because it's a dedicated unit. So you might be able to control the power there, but it might have even the higher latency and so on. Similarly, there can be a private 3D cache per chiplet, which is being currently developed. Currently, the AMD systems have this design. So you have private 3D cache per chiplet. That means that the CCDs have the 3D cache by itself. So you do the maximum bandwidth utilization there. You have the minimum latency. It's an easy design. Basically, it's an easy design. But there are talks to have another level of cache, basically the L4 cache, which will be a system level cache, and that might come up like this SoC cache, and it might be a 3D cache. The other aspect is that it's, so for example, if you make it per chiplet, it's not necessary that each of the CCD has to follow the same design. Some CCD might have the 3D cache, some CCD might not have the 3D cache, and so on. Okay, so I think that's what I had with respect to 3D cache. Let's come to what we are doing in 3D cache. So I worked on a bit on this 3D cache when I was at AMD. So I worked mostly in the performance verification side of it. But what we are right now doing is that we are taking some application. We are mostly taking this NLP applications, language models and so on, and try to see the performance behavior of working on this 3D cache. We have a real system which has got 3D cache. We have a desktop as well as a server. This 9000 series EPIC server, and we have a 7000 series AMD Ryzen system which has a 3D cache. We are profiling the benchmarks. We are seeing how much of hit rates or miss rate we are observing for specifically for the NLP workloads at this point of time. Furthermore, what we are also doing is that we are implementing a 3D cache interconnection network based simulation framework. And this simulator, I hope I can promise that will be much more accurate than the GEM5 simulator and so on, because it models, it goes up in a cycle accurate manner. Also, it models each and every queues separately. So to have a glimpse of that, so this is the I know the picture is not that good, but then this is the cache controller. It's a multi-stage pipeline cache controller. It's not a timing-based cache controller. It's a multi-stage cycle accurate cache controller, which has like 4-stage pipeline implemented. Also a superscalar memory implemented in it. So basically requests can come from any source. It can get distributed to any of the banks and so on, and then it can service the request to measure the actual latencies and actual bandwidth. So we have a queuing model, we have a pipelined and superscalar memory design. We have flexibility in terms of modifying the cache coherence protocol. That means you go ahead and implement the messy protocol. In order to go ahead and implement Moisey after that, it is very simple. You just add 4 or 5 lines and your system should be capable of going ahead and simulating a Moisey protocol and so on. So similarly, the integration with other cores and the memory is very simple, because it has got different ports and you just need to bind the ports, something similar idea we took from GEM5 and so on. Currently, the current status, the bandwidth tests are working if we are connecting 2 levels of cache over the network. And in the network, we have been modeling the switches, the static routing. Of course, we are just supporting static routing policies at this point of time, but we support the queuing model and the pipeline processing of the network packets and so on. So also we have implemented the fairness policies, and the cache and the network is currently implemented. Apart from that, we support a visual debugger. So that means you can actually see where, if some code is not running, then you can actually see where your packet has got stuck. Okay. What else we do? Actually, I do is I work on model checking also, formal model checking and statistical model checking of microarchitecture circuits. And recently, I have also started this performance projection of multi-core system using machine learning. I work extensively on cache coherence protocols. So we are looking for large system-based cache coherence protocols, and that is one of the major reason why I spent a lot of time implementing this cache simulator. Apart from this, look at the CXL.memory optimization, some performance optimization with respect to federated learning applications and so on. Okay, I think I will stop. Yes, thank you. Any questions?
Questions?
What exactly do you do on performance projection of multi-core?
So we are able to collect the perf data of the system, right? So now what we are planning to do is we will take those perf data, collect a good data set of the perf data, and project the performance of other systems with minimal differences in terms of architecture, and project the performance by running using this perf data. Will project the performance from the other perf.
What kind of models do you build?
Just started. We're thinking of applying some kind of transfer learning or something in that domain. I'm not an ML expert, just that nowadays students are very much excited about doing ML. So let's pick up our ML project and try to apply our thing there. That's what is the idea.
Any more questions? Okay, if there is no question, we can thank Devi once more.
Thank you.
named in this slide. So, actually, the students there are the main contributors to this work. So, I'm going to talk about application bloat. So, applications are often bloated, and what we mean is they are too big in size. So, this could happen for many reasons, like there's a lot of code in the application that is not actually used, or there's data in the data files associated with the application that are not being used. So these things cause bloat, and they increase the download time and the latency of the network, etc. And it makes it easier, harder to distribute software and share it easily. So code bloat is when you have dead code, lot of unused functions. This is our data bloat, as I said, is when there are data files that are not used at all, or the file is used but only small parts of the file is used and the rest of the file is not used. So that's called data bloat. Both are very prevalent in practice. So we are primarily targeting data bloat in this work. So although code bloat is also a problem to be addressed.
So Rajan, just a quick
Yeah.
clarification. When you say the data bloat,
Right.
is it that some parts of the data may not be accessed based on input parameters to the application? And you're saying this across all parameters?
Yes, I will be coming to that. What you're saying is correct. I'll be coming to that. Yeah. Yeah. So, what is a container? I hope most of us know what's a container. It's a bundling of software and data required into a package. Containers are now widely used to share applications between developers and end users because they encapsulate all the libraries and all the system requirements in one go and make it easier for the end user to just download and start running immediately. Right? But containers actually increase the problem of data bloat even more than other techniques in the past. This is a sample Docker. Docker is a very widely used containerization tool. This is a small Docker specification. What you can see is that the base image is Ubuntu. Actually, the base images themselves are very large, but that's a problem that we are not addressing right now. And then there is a couple of downloads of. This is the downloads the application, and this downloads a data set, and then it runs the application. This is a very simplified version of a Docker file. The problem we are addressing is in this data set. This is a standard data set provided by some weather agency, for example. These are very, very large. They contain all kinds of information. But this specific application may be using 1% of it or half of it, or so on. But these are standardized data sets that you don't really control. Various agencies are generating them. So what happens? So the developer may share the Docker file with the end user. Bob may share it with Alice. And when Alice runs this Docker file to create the image, it starts the download process. And that file could be maybe 10 gigabytes. And that Alice has to wait that long for the data file to download. That may take a few minutes or more. Right. And it will also increase the network traffic, increase usage on your disk and so on. So here is a vastly simplified program. Since I work on program analysis, and so since my hammer is program analysis, I'm going to use program analysis to solve this problem. So this is a sample toyish cross stencil application. So I hope we are all aware of what is a stencil program. Basically you have a 2-dimensional array or a 3-dimensional array. Think of it as an image, and you are going to traverse over parts of the image and do some aggregation operations. And so this is a program with two parameters, step x and step y. And this harks back to Jayan's question. So there is a condition in this program that step x must be basically less than equal to step y. Otherwise the program is going to just return. It's not a valid configuration of these inputs. If the condition is satisfied, it starts off at, so I equal to 7, j equal to 0 is basically this corner. So the I value ranges this way and the j value ranges this way. So it's going to start here, and then it's going to do a walk over the array and do a stencil calculation, which we will see by animation. So read ij would read this cell, because I is 7 and j is 0. And then I plus 1 is the next cell, and This is this cell. So in each iteration, it reads 4 cells, a square of 4 cells. And then you reduce the I by step x, which is the parameter, and increase the j by step y, which is the parameter. And if step x and step y were both 2, these are the cells you would access in this run of the program for that parameter valuation. Now it's if step x and step y were 2 and 3, these are the cells you would visit. It's easy to see that because of this condition, these are the only cells you would ever access in any run of the application. Sometimes applications don't have such conditions explicitly, but the developer or the end user may have an idea that anyway I'm not going to provide data parameter values outside a certain range. In that case also the same issue arises, that there will be large parts of the data that are never going to be accessed. If the end user has a requirement that they anyway not going to supply certain parameter values outside a certain bounds. So our plan is to somehow find out which part of the data can I want to produce another data file from the original 10 gigabyte file upfront, carve it and remove parts of it, and put the URL to the carved version so that the download will be faster. Right? So I want to upfront produce a subsetted data file and use that in the container specification. That's the overall plan. So this is read as unused data in all runs of or in all desired runs of the application, which is almost in this case about half of the data file. So the problem definition is given a program, it has two kinds of inputs. These are the parameters, which in our case was step x and step y, and this is the data file. So I am not calling this input. So technically I am just referring to the parameters as inputs. And this I am calling this the data file. And this is the result. So for example, this theta could be step x and step y, and 5, 6 is one possible valuation. Just a sample parameter values. By theta all, I mean the space of parameter valuations that are relevant to this user. So in this case, so here it means all valuations of step x between 0 to 10 and step y between 0 to 10, or it could be in our example, all values where step x is less than or equal to step y. So this theta all is the space of parameter valuations of relevance. And we may not know this upfront. It may be a condition that's hidden in the program. That is the main catch. So this may not be known upfront also. It may be hidden somewhere in the code of the program. The program source code may also not be available. So we don't know this theta all necessarily. So what is the problem statement? Given a program, the theta, well, okay, this theta all is not actually given, but to define the correctness of the transformation, I'm assuming that this theta all is available, but it's not really known to us. And the original data file D, the plan is to produce a debloated or subsetted data file D double prime, such that D double prime is a subset of D, and for all parameter evaluations in this theta all, which we may not know, the program, when run on this parameter evaluation on the subsetted data file, leads to the same behavior as if you ran the program on the full data file for the same for every parameter evaluation in this theta all. So is this clear? This is the correctness of the desired transformation.
So we're not looking at the distribution of theta or theta all. It's just yes or no, whether it's within the theta all or not. We're not looking at saying that some input values are very rare and therefore.
No, there is no such notion here. It's binary. It's either in or out here. So basically, intuitively, the program should be unaware that the data file has been carved. By the way, when you send the carved file at the runtime end, or maybe I'll come to this point later. This is something to be aware of, but I'll touch upon it later. So there is some past work which is called low fidelity tracking. They only find out which files the program can access, but not which parts of the file. So the entire file will be either kept in the package or not, but that is very coarse grained. with a very large file, if even a small part is accessed, they're going to say the whole file is in the package. So we are going to try for a fine granularity carving in this work. And this is the first work which does this work of carving a data file to a fine granularity, and so giving higher savings compared to previous approaches. So what is one naive way of doing? I mean, even if, let's say we know the theta all, which we may not know. If you knew the theta all, a naive way could be to run the program on all values of theta in the theta all and see what all parts of the array are accessed. But first of all, we may not know the theta all. Even if we know it, this may lead in too many runs. If both step x and step y can take values 0 to 1000, that's 1,000,000 runs, which is prohibitively expensive. And if the parameters are floating point numbers, it's even more than that. Even small ranges can make it completely infeasible, this kind of plan. So you can't really do a brute force approach like that to do this. So our insight is that usually one or more convex hulls of regions within that data array are accessed across all parameter evaluations. So can we optimize the process by somehow finding only the boundary points of the convex hulls that are accessed, and then just assuming that everything within those convex hulls are going to be included in the carved set? So can we produce a small number of runs which will cover the boundaries of these convex hulls and be able to fill in the rest analytically? So that's the intuition behind the idea. So this work is not based on static analysis. For those who know what is static analysis, this is not based on that. It's based on running the program and observing what it accesses. So with this program, due to this condition, so if this is the range of parameter evaluations, so step x can range 0 to 8 and step y can range 0 to 8. But because of this condition, step x is less than or equal to step y, these green values are the theta all. These represent the parameter evaluations that are interesting for this program. Set of interesting or useful parameter values, but we don't know this set. And this is in the array, this is the part that is accessed across all runs on parameter values in this green part. So a couple of things you can see is that there is no easy structural relationship between this shape and this shape. It's not necessarily the case. And also we don't even know this shape most of the time to begin with, because this condition may be buried somewhere deep in the code, or the condition may not be just in the beginning of the main function. It may be distributed throughout the code. So it's very difficult to get this. And also there is no clear correlation between this space, the space of parameter values in the data array subspace. So these are the challenges in this work. If we can somehow generate runs of the program which access, say, these corner points, and then maybe a convex hulling will find the rest of the region. So this may give us substantially fewer runs than we would have to do otherwise. So in this kind of made up situation, these two runs alone will actually visit all these corner points. So this is the run with step x is 0 and step y is 2, this run. This is a run where both are 2. It turns out that these two runs alone will visit all these corner points. Whereas the actual total number of runs is something like, even in this simple case, it's 8 to the power 64 runs are there in this scenario itself. So, yeah, so I think I went over this. What are the challenges? We don't know the theta all space, we don't know this space, we don't know this space. There is no good correlation between these two. The source code may or may not be available, only the runtime may be available, the binary, etc. Right? So,
Bhagavan, you
yes.
are assuming that the data is arranged in some form and the accesses are made.
Right.
But in the context of a file, it is sequential.
Right.
Correct? So, in those cases, would these analysis or would these techniques, how would these techniques kind of translate?
So I'm going to assume either a system call intervention or a change in the library. So typically libraries are used to access these data files, HD5 and other libraries.
Right.
Because this HD5 library, for example, gives you a matrix view of a sequential data file
So that
to make the programmers work easier. Like. So I'm going to assume that either you put some instrumentation in the library, which will tell you which parts of the data file are eventually being accessed, or a system call intervention to get the same information. Does that answer your question? Yeah.
We can even map the file and even page level we can see whether idleness is there or not.
Okay.
That can be one way.
Okay. Okay. Yeah. Okay. Fine. I mean, yeah, that is a little bit outside the core of this talk. How to get those offsets? There are many ways of doing it. Yeah. So one trivial idea would be to generate parameter values randomly. Some number of values run, but you may cover too little of the data file this way. And the danger is, so now I must mention, if you carve more of the data file than you should, then at runtime some data will not be available, and you'll have to throw an exception. Now, some little overhead is there anyway in this. You have to track, is the data there or not for after carving, because earlier that was not the problem. Every data was there. So you need some runtime tracking to see if is the certain IJ access available in the carved or not. And if it's not there, you have to throw an exception. So we want to minimize we can't guarantee actually in this work that you will never miss any data, but we want to completely minimize the exception rate.
So many of the applications have implicit assumptions about the data. For example, it is sorted on a particular column and so on.
Right.
So when you remove this data bloat, could it destroy the physical ordering which
Yes.
implicitly the application had assumed?
Yes.
Therefore, you now get an error which should not have occurred.
Yes, so yeah, that's a good point. We have not touched upon those things. One idea is that if there is a separation between metadata and data, maybe you should not disturb the metadata part, not while carving. If there's a clear separation of metadata and data. So this is one care you can take, but I don't know if it's going to be enough in every case necessarily. Although we have thought of this issue and there's also more future work to be done in this line. So we'll address some of these issues there also. So random sampling may not cover enough of the data. So our idea is to do a more intelligent sampling. So when I say sampling, I mean generation of parameter values. So this is our idea. So we first randomly sample, this is the space of parameter values. This is not the array. So this is the step x, step y parameter values. So we will initially randomly generate some points. We'll run the program on all those 7 runs. We'll see. So on these runs, there will be no, in the white part of the runs, there will be no data accesses because those are outside the theta all of this program. So we call such parameter evaluations useless in the sense that they don't cause even a single data access. And we call these useful because they cause at least one data access. So this is a segregation, and at runtime we'll notice, is this useful or useless? So then we know that these 3 are useful and these 4 are useless after the random sampling by running. So our idea then is to, I'm just quickly summarizing the idea without presenting the technicality. So we want to find for each useful and for each something, I don't have a phone here. Okay. So for each useful parameter valuation and for each useless parameter valuation, that is close. So these two, for this one, this is the closest. For this useless valuation, this is the closest useful valuation. So I have drawn straight lines to show pairs of useless and useful inputs that are close to each other. And my idea is that I want to give higher priority to generating new parameter values at closer to the midpoints of these segments. And this is a probabilistic sampling. So I'll give more weightage to sampling parameter values here and less closer to, so I'll give less weightage to sampling values closer to existing ones and more to things which are in the middle of, between a useless and a useful. And the idea is I want to find out intuitively the border of which are the. So remember that I don't know this green rectangle a priori. It is just. In this case, I know it because I wrote the program, but it's not known in advance. We are trying to guess that region exactly. So this way we make it probabilistic and generate with higher probability sample values closer to these mid zones and lower probability sample values which are away from the middle of these zones.
So in this case, you have a nice 2D shape.
Right.
Suppose in a high-dimensional space,
Right.
finding those cutting hyperplanes would probably be very expensive, right?
Well, it's just you need to know the Euclidean distance coordinates between
There's
2
a very
points.
large number of dimensions, right?
Right.
In any program.
So we have not seen more than 3 actually in these data sets. In this weather data sets, we have looked at various real data sets also.
And the approach kind of optimizes on, I mean, you're more looking at reducing the space rather than, it means on the other side there could have been useless space which you are not trying to remove, right? Like between 2 useful points,
Right.
there could have been regions which may not be useful.
Yes, you're saying.
That you are not focusing on.
Sorry, I didn't.
So, no, the reason that you said that you are trying to focus between
Yeah.
midpoint between the two.
So the intuition is that closer to the very close to the useful ones, they are likely to be useful.
That is true.
That is an intuition. And very close to the useless one, they are likely to be still useless.
Okay, okay.
So that is why we are increasing the probability of sampling at the midpoints.
And you are assuming between 2 useful points, all the data points will be useful.
I am not assuming anything. This is a heuristic to generate.
Correct.
Yeah.
That heuristic kind of says that, okay.
Yes.
Everything between
Yes.
two-
Yes. Between these two. Yes.
Okay,
Correct.
yeah.
That is
And
the.
you are not trying to prune anything out there.
Yes. Yes.
Got it.
Yes. Same between 2 useless. I'm going to assume they are all useless. Yeah. That is the intuition. Yes. Yes. It may not hold in every case. Hopefully, it will hold mostly. Yeah. So then we kind of repeat this cycle. So then we sample. Maybe these are the new sampled points closer to the midpoints. So then we throw these in also. We run the program on each of these. Some of them will be useless. Some of them will be useful. And we iteratively continue this process as long as the time budget allows. And finally we'll have a set of useful points and a set of useless valuations. Then we will run the program again on all those useful valuations. And that may give something like this. I mean, this is more like it may give something like this. So now this is the data array space. So all those useful ones which I collected, when I ran across all of them, these points of the arrays were accessed. Again, you'll see a lot of white space. These are probably because we didn't generate enough useful samples. So the idea is we'll do some convex hulling to include more. Otherwise, we may have very poor recall, right? And so, how much time do I have, Sumit? 10 more minutes. Okay. So if you do one single, if you do one single convex hull around all these points, you will get a lot of extra. You may get a lot of white space, which is not accessed at all. So that may reduce the carving efficacy. You may not carve much. So this is where the student came up with a rather clever idea of finding a set of convex hulls rather than one convex hull. So this is like a fight between recall and precision. If you cover too little, you are going to have a lot of exceptions. If you cover too much, you don't get much carving. So this is like a heuristic attempt to come somewhere in a sweet spot here. So the student made this idea of first starting with very small convex hulls and then merging nearby convex hulls. And he had a metric for when do you consider two convex hulls to be near each other. Then at some point he'll stop merging because they are kind of relatively far from each other, the convex hulls. And if this is tunable, he has some parameters for you to tune to decide whether two convex hulls are close to each other or not. So this was the end result in this case, whereas naively it would have been this entire chunk. So I'll go to the results. So we used a bunch of most of the experiments are done on a bunch of synthetic benchmarks. This is called a H5 bench. This is actually used by a lot of researchers, although the benchmarks are synthetic benchmarks. So this is mostly used by people. So H5 means the HD5 is a very standard format for representing these matrices as files. So H5 bench is designed, so it's a set of programs that use the HD5 library. So it's a standard benchmark suite. It has situations like this. Like this program accesses, so this is a data array. So this program accesses only 2 corners. This program accesses margins of the array, etc. These are different shapes of accesses of the programs in that benchmark suite. We also did one experiment with 2 realistic programs, more realistic programs. I don't think I have those in the slides here. Those are climate modeling, and one was something scientific data from the space. But we didn't run it on the 2 actual programs, but we kind of rewrote those 2 programs in a simplified way. But we used the real data set. What I'm presenting here is based on these synthetic benchmarks. So shall we, okay. So these are the baselines we considered. One is brute force, which is you try to run on all parameter values in theta all. So here we assume that we know theta all at least to be able to do the brute force evaluation. Otherwise we can't even do it. So brute force need us to know this, so we will supply it to brute force. But there is a time limit we impose, since the actual brute force could take months. So there is a, I think, few minutes time limit we impose. It's the same time limit we impose on all the approaches. And AFL is a code coverage tool. I will not really go into how it works. It is a fuzzing tool which, given a program, can generate inputs for the program. But its objective is to increase code coverage. So it's a test case generation tool. So the hypothesis is, does code coverage also imply data coverage? That is the question. So that's why we chose that as a baseline. So I think precision and recall, I think we kind of know. Recall means how much of the actual accesses that you should cover did you cover. And precision means how much extra did you include in the data array which you need not have included. That is the, so I'll show some charts. This is the average recall for a fixed time budget. I think we fixed it to few minutes because these are small programs. And so this is blue is our approach. This middle bar is AFL, and this is the brute force, the green one. So as you can see, our recall was pretty high, 1 in this case and almost close to 1 in this case. So the other approaches suffer from very poor recall.
But if you had run brute force for infinite time, that would have reached 1.
Yes. Definitely it will reach 1. AFL may not reach 1 even given infinite time because of the heuristics in AFL. So the one, yeah. So when you have, so about in about 1% of the space we did not cover, and actually we checked whether, so what percentage of sample input values does that represent? That also was around 1%. It's actually less than 1%. This means that 99% of parameter values in the theta all actually cause no exception. That's what this means.
But if you run the brute force, how do you know what's the ground truth?
That was manually fixed by analysis of the code. So about 1% of the data file we missed, and that also translated to about 0.8% of the parameter values led to exceptions. So we don't have full recall, but we came very close. So this is precision for a given time budget. So precision should be high, meaning if precision is low, it means you are including data that you need not have included. So the AFL and the brute force, they always have 100% precision because they are not doing any convex hulling at all. They are identifying data that was necessarily accessed. So they are never going to include even one data item which was not accessed. Because they are simply based on running the program so many number of times on inputs and seeing what parts were accessed. So you cannot have any extra data accesses at all. So they have 100% precision, and our precision is somewhere between. So this means that 60% means maybe like I think maybe there was 40% extra data that we included in the array that we could have carved out. So higher precision is better, and this is actually a more simple convex hull scheme. I think this is a scheme where we just do one convex hull instead of a set of convex hulls. This is like another baseline. So if you do only one convex hull, again the precision is low. It includes a lot of extra things. So the precision appears good, but we have to keep in mind that the recall is very poor. So it's like, so there's not much use having high precision when there will be so many exceptions at runtime with a poor recall. And this was a final experiment where we did, if I give more time to them, will they achieve high recall to the other tools? So this is a log scale of time. So as you can see, if I give 100 times or 1,000 times more time, so this is a log scale. So this is 1, this is 3, means 1,000 times more time. Then they achieve. This is AFL and this is brute force. So even with, brute force we cut it off here because it was, I think, so AFL with, when you give 1,000 times more time, you got similar recall. Brute force did better, I guess, in this case. In this case, both are high. Right. So you need to give a lot more time to achieve similar recall with other tools. So here's a bunch of related work. I will not go through everything, but one thing that might be interesting is fuzzing is a related work, AFL. Fuzzing means generating data inputs, usually for code coverage, not for data coverage. And invariant inference is also an interesting area of related work where they try to find out what are the relationships between program variables within a program. And it has a connection to this problem because we want to find out basically the relationship between the IJ, the data access subscripts at the point of data access. So in a way it's related to the invariant inference problem. So I'll stop with that, and there is a whole bunch of future work that can be done in this area in improving this approach. Here we make some assumptions that we can track the file offsets easily. What if you can't track file offsets easily? One can do more related future work on doing such things also.
Okay, thank you. Questions?
The picture that you showed was essentially like a binary classifier between useless and useful and so on. Could you have used the classifier techniques to do the separation rather than doing the geometric approach, which is to use the convex hulls and so on?
What would a classifier?
You had the data. You had the useless and
Right.
So you could have trained a classifier to decide what is the separation hyperplane there.
Right.
And instead of using the geometric approach.
Right. Instead of doing a convex hulling. Yeah. Yes. This is actually work that we are ongoing work actually. I don't have a latest update on how far this went, but it's already a thing that one of the students, not in IISc but elsewhere, is engaged in collaboration with us. Yeah.
I probably missed it, but what is the basis for that intuition that something which is useful and you generate a point which is nearby?
So the basis is that you want to know this green part basically.
Correct.
If you knew this green part, even then, it does not fully solve the problem because there are still too many runs, but the intuition is that you don't know this green part and you want to know it. So, and the intuition is that the boundaries of this green part are more likely to pass through the center points of these shortest segments between useful and useless points, and not as opposed to being very close to the known useful or the known useless. So that should accelerate the process of finding the useful and the useless inputs.
Any more questions? Oh, if there is no question, then we can have another round of applause.
Thank you.
And our department is a
Oh,
small
okay.
from this side.
This side?
Only spot.
Okay. Thank you. Thanks for having us.
And Qualcomm Faculty Award 2094. Over to you, Vishwa.
Thanks, Sumit. I hope you can hear me. Last row. Okay. So I know all of you are waiting for high tea. So my talk will be the bridge between your high tea and my, my curiosity and my excitement about talking about my research, right? So although Sumit talked about microarchitecture for performance, so this talk is about security and how can you design secure processor or secure systems with some of the obvious ideas that the community is aware of. So that will be the part of the this talk. Okay, so computer architecture is a field from last 3-4 decades that the primary metric of all these research activities is performance. Right, you take any computing device, the metric of interest is performance. Right, and then all the speakers talked about performance throughout the day, so I won't spend time on highlighting how important performance is, right? So these are some of the ideas which are there from last 40-50 years, improving our single thread performance. That's the metric that we are interested in. But then, what about security, right? And when I say security, I'm talking about microarchitecture security. So the idea here is, through this microarchitecture ideas or microarchitectural techniques, can you cause information leakage, right? And whenever you try to come up with secure microarchitecture design, it's not a free lunch for you. You have to pay the price, and suddenly you will start seeing performance drop, right? So all the research that people have done from last 30-40 years in improving performance will now go for a toss just to provide security guarantee. Okay, so that will be the theme of this talk for next 32 minutes to be precise, right? So if you go and talk to all these big companies who are designing secure processors, right? And if you say that, okay, I have an awesome idea which will make sure that all the processors are secure, but it will cost X point Y% performance drop, where X is more than 1%, they'll say they're not going to buy it, right? So what they need is, you need to provide security, but not at the cost of other conflicting trade-offs like performance, energy, power, area, and storage, right? So with that, I will start with the first part of the talk, which is securing the last level cache. So as John, Devi already talked about multi-core systems and the notion of last level cache shared by multiple cores. So although this provides a pretty good trade-off in terms of data sharing across multiple cores, it is also a playground for information leakage, right? So I will show you how exactly information leakage can happen at a 50,000 feet view. So let's assume there are two processes running on core 0 and core 1, and this guy is actually a notorious guy. What he does, he actually tries to fill a particular cache set at the last level cache, right? So our last level cache are like 16-way associative cache. So this guy will fill that particular set with 16 addresses, right? And now let's say the victim comes. The victim can be anyone, including some of the cryptographic library. And if the victim is also mapped to the same set, it will start kicking out the lines that are brought by the spy, right? And the threat model is, in future, this guy will come again and try to time the accesses, right? And if it sees hit at the last level cache, which means no one has actually kicked out its lines. If it sees long latency, which means the lines are not there, which is part of the spy process, someone has kicked it out, that's why it has to go to DRAM, right? So the latency difference is actually an indicator here for some of the secret dependent data, right? You can assume long latency can mean 1 and faster latency can mean 0, okay? So this is the bigger picture that you should keep in mind at least for 5-10 minutes, okay? So how to defend, right? So one way to mitigate this so-called conflict-based attack is that you make sure, given an address, the location at which the address map to is non-deterministic, right? So the address to set mapping is non-deterministic, so that the address can go to any of the sets. So that actually breaks the determinism, and because of which it actually breaks the notion of conflicts, because now the attacker won't be able to know which set is actually carrying the victim data, and every time you send the address, it actually maps to another set, right? Dynamically. Looks promising. This idea actually got best paper award in Micro 18, right? So it must be pretty cool. Within 6 months, this is broken. So this idea is broken. People actually attacked it. They said, no, we can actually recover an IISc key even if this mitigation is on. And then the series of cat and mouse game continues at least for next 3 years, right? So more and more randomized cache ideas came. They just try to make the life of an attacker difficult. But finally, within a few months' time, someone else will come and say that, okay, if I have a new attacker, which is much more agile, then I'll be able to break it, right? Sorry.
Good question. You are having information leakage, but the bandwidth is so low. Leakage is not really an issue because you get 1 bit per day or something like that. Then you really won't care too much about it, right?
Yeah. So here the bandwidths are in 100 bits per second kind of, right? So last level cache, right? So it is still, I think, still a point of concern. Right? Yeah, obviously, if it is 1 bit per day, definitely we want, right? Okay, so the series of attack and mitigation continued, and the idea behind all these proposals was, or the motivation behind all these proposals was to make sure the attacker won't be able to cause any conflict-based eviction, right? So for a given set, if there are multiple processes mapped to that set, how to make sure that the attacker won't be able to kick your data out and measure the latency difference, right? So that is called set associative eviction, in short SAE, right? So what's the solution? Even if it is impractical, you can actually go for a fully associative cache, which is pretty intuitive, right? So then there is no limit on your associativity. Your data actually can go, or your address can go to any location. Sorry.
How does the latency tell you the data in the bit?
No, the latency doesn't tell you the data in the bit. The latency tells you whether your addresses are kicked out or not, right? And then you have to do some bit of post-mortem analysis to understand if these addresses are kicked out, what it corresponds to in my victim's program.
Not the data, but the addresses of the victim too.
So that eventually correlates to data. So let's say I have an AES key, 256-bit key, right? And they are data dependent accesses. If the bit is 0, then you access address X, that address X mapped to set number X. So now I'll create conflict in set number X because of I know that this is actually mapped to address X, which is caused by secret bit 0. That's the story.
For certain classes of applications.
Wherever you have control flow based data accesses, you will be able to do that pretty easily. Okay. So, but yeah, that is one of the easiest one to attack. Right? So that's why crypto folks, they do constant time programming. so that you won't be able to get that data dependent based accesses. Okay. Yeah. So as I was saying, the idea can be you design a fully associative cache, which is impractical because last level caches are in tens of MBs. But still, if you do that, you'll be able to guarantee that the attacker won't be able to kick your addresses out from the last level cache deterministically, right? Because once you have a fully associative cache, it gives you a complete address space to play with. There is no deterministic mapping that this address is mapped to this location, and replacement policy becomes random. You can't apply deterministic replacement policy in a large fully associative cache. Okay. But obviously this is not practical. But what people tried is, can we design fully associative randomized cache, which will actually give you the illusion of a fully associative cache, even if it's not, right? And with all the trade-offs in mind, right? So if you go for a fully associative cache, your access latency goes up, your power budget goes up. So how can you make sure that you respect all these trade-offs? Okay. So this is the idea that came in Unix security almost 4.5 years ago. And in the interest of time, I'll give you the 10,000 feet view of this idea and why it provides security. So in our cache, we have what is called data store, where the data is stored in the form of data entries or cache lines. And for each data entry, you will have a tag entry. Right? So every time you send a request, you first compare your tag bits. If you get a hit, then you go for the data. Right? What this paper suggests is you decouple the one-to-one mapping between tag and data. So now they are like two independent microarchitecture structures, and then they added extra invalid tags just to fool the attacker, right? So for every set, now you will have extra few tags appended with each set, so that every time you create a conflict, you will have an invalid tag to replace. And remember, now the replacement here doesn't correspond to the replacement there. So they are decoupled. Okay. So this breaks a dependency, and if you go for a global random replacement there along with extra invalid tags, the paper actually provides some guarantee that if you try to mount an attack, it will take 10 to the power 16 years considering the latest Intel and AMD machines. Okay. So this is the argument here. So if you provide extra 5 invalid tags, right, for every set, this is giving you a guarantee that you are not seeing any set associative evictions. That's the goal. Okay. But then what's the problem? So if you look at this trade-off, it actually mitigates completely all the conflict-based attacks, right? At least so far, it's been 4.5 years, no one has actually broken it, right? And performance is also similar. So the conflicting trade-offs are actually, they're happy. But if you look at the storage area overhead and the power overhead, they're actually significantly higher. 20% is actually a big number. Okay? So what we did, we tried to optimize these two parameters or these two metrics of interest so that we can provide security, but not at the cost of power and storage and area. Okay? So the idea for the proposal that I'll be proposing in the next few minutes actually came from a very old microarchitectural insight, is that in a large last level cache, most of the lines are dead on arrival, which means whenever they come, they don't get a reuse. Right? They come once and that's all, they will get kicked out, which means the utility of those lines are actually 0. So it's okay if you don't cache them at the last level cache. Okay? And if you look at this plot, almost 80% of the cache lines in non-secure baseline and also in the secure Mirage proposal are actually dead, right? So by looking at this plot, you will have an obvious solution, and the obvious solution will be, can I actually reduce the size of my data store, right?
So does that mean that the working set fits in the L3 cache?
No. It doesn't mean that the working set fits in the L3 cache. So we have multi-levels of cache, right? So the prominent reason for getting this deadlines is that most of the time you'll get L1, L2 hits. So the L3 cache line will become colder and colder, right? And before you get a reuse, there's a high probability that it is getting kicked out. Right?
No, but these are included, right?
No, it's not inclusive.
Everyone
No, no, no.
It's more that the either the data is a streaming data, or the reuse distance is so high, that by the time that you want to get it back, it is not.
Yeah. Right. So the reuse distance is actually larger than the LLC capacity itself. Okay. So this is the insight. To carry on for next few slides. So we start asking, can we reduce the data store size, right? And just to take care of the extra storage that the Mirage paper had, right? So this is again the 50,000 feet view of our idea. What we did is, so this is our idea called Maya. If you look at the difference, the data store now becomes smaller. Okay? Tag store looks similar, but there are a few extra boxes with different colors. Okay? So this idea has these boxes for security, right? Extra tags, invalid tags. We have those, but we have few extra tags to track reuse. Okay? And only when we know that the particular cache line address will be reused, we will allocate a data entry here. Okay? So this idea was actually pretty, So if you look at the utility of this idea, we are able to save storage, forget about storage overhead. Right? So why and how, I will show you in a few minutes. So the key here is, remember these are cache lines which are of 64 bytes, but these tag entries are actually of less than 8 bytes. So which means for a single data entry, you can actually pack 8 tag entries, right? So the data entries are more costly in terms of storage and area, right? So if I can kick out one data entry there, I can put 8 tag entries here, right? And that can actually provide me a sweet spot. Okay, so this is not a new idea, at least in the microarchitecture community, people have done many work tracking reuse. So this is one of the simplest idea. So on your first axis, you don't allocate the data in your last level cache, you just allocate a tag entry. Okay. On a future axis, you will get a tag hit but a data miss. Okay. That time you bring your data into your last level cache. Right. This is the way you will track the reuse. Right. And this is what we did, but now for security. Right. We have extra tags for security guarantee, extra tag for tracking reuse. And we'll finally show that this is the overall design. We had randomized functions to make sure that the address to set mapping is not deterministic. They are still decoupled, but the data store becomes smaller. And there are extra tags which compensates the space that we have saved from data store, which gives the additional tag store entries for tracking reuse, along with security, right? And I won't go into the detail in the interest of time. So the security model that we had to argue that this is indeed secure is the famous bucket and ball model. So here buckets are actually your sets in the last level cache. Balls are actually your associativity. Sorry.
Quick question about the earlier numbers. You showed that there were 2% savings
Sure.
in storage, but you had earlier mentioned that the last level cache had a huge number of dead on arrival kind of things. Would you have expected the number to be higher than 2%?
No, so our goal was to provide a sweet spot where we won't lose performance. So if I actually start providing even a tinier last level cache, my performance will go for a hit. Right? So let's say I have a 16 MB cache. What we proposed is 16 MB data store becomes 12 MB data store. We make sure that the overall storage area is same as the baseline without any performance penalty. If I make it 10 MB, I'll start seeing performance hit.
So the sweet spot you are seeing is that 2% where
I can actually reduce a bit, but I won't get extra security guarantee. So why should I do that? That's also another argument. Okay. Okay. Let's move on. Sumit is looking at me.
He wants to evict you.
Yeah. I don't mind, but anyway. Okay. So the model here is you have the sets as buckets, and you actually throw accesses as balls into your buckets. The goal of this work is to guarantee that you won't get a ball spill. No matter what the attacker does, you won't be able to create a set associative eviction, which is actually ball spill. So you have to write a proof of 1.5 pages to argue that this is indeed the case, and we also showed it quantitatively, right? Okay, and we also argued that with this new additional tags which tracks reuse, you won't be able to create new attacks. Otherwise, this cat and mouse game will continue again after 4 months, right? So far it's been 8-9 months. We presented it in IISc, so it's been 7 months. No one has attacked it so far. So I can vouch for it so far, okay? Yeah, in the interest of time, I won't go into the details. These are the numbers. It shows that there's a few marginal performance improvement here. You have to look at the right one, the Maya one. That's because of the reuse. Nothing to, nothing from the security side. And this is the trade-off that is interesting. So compared to a non-secure baseline, you still get performance improvement, and you get savings in all the conflicting trade-offs that any architect can think about, right? And finally, yes, we argue about security. Right? So it's like a happy family of trade-offs that you can think of at the end of the day, right? Okay, so this is a summary. We exploit a pretty well-known feature or a insight of reuse. We try to use that for security. We guarantee that if you use this cache, you won't be able to mount an attack, at least for 10 to the power 16 years, right? Yeah, and it provides a sweet spot in terms of all the trade-offs that you can think of. Okay. So attack vector 2, and maybe I'll talk about it for 10 minutes. So the previous attack vector was for a multi-core system, and this attack can happen even in a single core system. Okay. So these are called transient execution attacks, and every few months, if not few weeks, new and new version of transient execution attacks are coming in, attacking different parts of microarchitecture in modern processors. So what this Spectre attack, which is pretty famous, almost 3,000 citations or maybe more, what it does, it actually exploits what are called the speculative execution and out-of-order execution in a modern processor to leak sensitive data that was not supposed to be accessed in a secure processor. Okay, and we'll see how exactly it happens at a 10,000 feet view. So this is a code snippet. When you have this kind of statement, again, control flow, right? So this if condition, it can have true and false outcome depending on the value of x and array one size. So whenever you have the if statement, modern processors will actually call a structure called branch predictor, and this branch predictors will tell you whether this condition will be true or false. Based on that, they will tell you, okay, go ahead and start executing it. Okay. So as an attacker, what you can do, you can actually mistrain this branch predictor by sending, x values which will help the branch predictor to be mistrained, right? So, for example, if the array one size is 5, you keep on sending value of x less than 5, right? So the predictor will assume that every time I see this if condition, I'll actually take this branch. But then attacker will actually send a value which is actually greater than array one size, right? But the predictor will say no. In the past n number of iterations, you actually provided legitimate value, so I will let you go. So now the magic happens. You start accessing all this. This is actually the secret array, which is not mapped to even your own address space. Your OS doesn't allow you to access. Okay, but now because the processor has started executing it speculatively, the address and the data is now sitting in the cache, right? And the previous attack that I talked about, right, conflict-based attack, once the address and data is there sitting in the cache, you can actually create a conflict-based attack to reveal the secret, right? So that's what it is. So this is the high-level picture of what exactly happened in a modern processor. You have multiple instructions. They enter the processor in order. Like this is the order that the compiler has generated, but the processor will actually execute them out of order, just to improve throughput and parallelism. But finally, you need to leave the pipeline in the same order in which you entered, just to respect the compiler order and provide a precise state for your processor, right? And if you get a branch or the if condition that I talked about, even if you know that you have actually made a mistake, you don't actually react immediately. That's the semantics. That's the design. Okay. you will react when this instruction actually leaves the pipeline. And that gives you a window to play with, right? So within those, depending on the size of the structure called ROB and other structures, you may get a 100 200 cycles window where you can actually get the speculative data into the cache. Okay. So far so good. This is a complete picture where, as an attacker, you actually first trap the branch predictor, and then which actually force to access these addresses that you are not supposed to. Now they are in the cache, and then you do any cache attacks to retrieve the secret. What we looked at is we looked at all the architectural mitigations that appeared in all the flagship computer architecture conferences, tons of papers. We looked at the best one among all the mitigations that are proposed in terms of, again, performance, storage, security, energy, blah, blah, blah. So this is a paper that appeared in Micro 21, which is called Ghost Minion. I'll show you how exactly it works. So this was the playground for mounting the Spectre attack. Even if you get the data speculatively, you have to put it somewhere to play the game, right? This paper, what it does, it says if you are getting some data speculatively, don't put it into a cache hierarchy. Instead, you put it in a small tiny cache called Ghost Minion cache. Okay? And every time you do a context switch, let's say one process comes, another process goes, you squash the Ghost Minion cache, which means your L1, L2, L3 cache, they are still having the same state, unaffected by speculative access, right? And that provides security by definition, because your cache is not touched by speculative access.
But we should monitoring the fact that it's speculative data or not itself would be a serious overhead, right?
Not really. Not really. Right, so there are actually pretty intelligent ways to find out whether it is speculative or not speculative, right? Yeah. Okay, so the new hierarchy looks like this. These are the cache levels where you store data which are safe. Okay, this is the level where you store speculative data, right? And whenever the CPU requests the request for data, it actually goes here. In the speculative path, it can get a hit in any of the cache levels. But if you get a hit, you don't change the state, not even the replacement policy. But if you get a miss, you get the data from DRAM and directly go to Ghost Minion, bypassing all this. Okay, so that's the cache hierarchy. Yeah, that's the path that I talked about, right? So, and finally, what happened when the instruction becomes safe, which means it's no longer speculative, then you start putting those data back into your hierarchy. Okay? So they will go like Ghost Minion to L1D. When you get it out from L1D to load L2, then L3. Okay. So there's like additional traffic that is going on just to provide security. Okay. So what we asked a few years back is, can we come up with transient execution attack through prefetchers? Okay. So prefetchers are structures sitting beside cache, and they look at past accesses and speculate about future accesses. Okay. Now, you can also come up with transient execution attack through the prefetcher. If the prefetcher is looking at speculative accesses, this guy will speculate further, right? And bring more and more speculative data into the cache. So when we started working on it, we didn't have a proper attack to showcase, right? But by the time this paper appeared in Micro, we found 3 attacks appeared in Unix Security and CCS, saying you can actually indeed attack through a prefetcher. Okay, so I will show you how to design a secure and yet high performance prefetcher. Considering we have less than 10 minutes, we actually look for the prefetcher that we proposed in Micro 22. This is called Bertie. So as I said, the goal of the prefetcher is to predict the future addresses accurately, right? And this prefetcher, what it does, the way to look at the slide is you look from left to right. These are the addresses that the cache is getting, 2, 5, 7, 10, 12, 15. And if my goal is to convert the address 15 into a cache hit, when should I start prefetching? That's the precise question that we are asking. So you can actually prefetch from 12 with a stride 3 or 10 with a stride 5. What we did in the Micro 22 paper is we looked at how much time will it take to get the data for that address 15. And the latency is variable because the memory hierarchy is out of order, right? So if you look at the fetch latency for address 15, it says that you should actually prefetch when you get the address 2 or 5 with deltas of 13 and 10. This is the prefetcher, okay? Now if I have to make this prefetcher secure, what will happen? You can say that now you can't do speculative prefetching because it will bring speculative data into my cache. So what I can do is I can actually go for on-commit prefetching. Like whenever the instructions are safe, then only I will prefetch. Right? What's the cost of it? 11% performance drop. So these are across all the prefetchers, including prefetchers which are there in the modern systems. Right? And just to highlight this trend, if you want to work in prefetching, getting 2-3% improvement itself takes 2-3 years. Right? Now it's 11% drop. So you can assume this is a decade of microarchitecture research. Right? So our goal was to bridge this gap, but without affecting security guarantee. Okay? So we found 2 insights. First one, I gave a clue while explaining the memory hierarchy that there are extra traffic. There is extra traffic that is going into outer levels of cache just to ensure security. And now that we can't prefetch immediately when the request is actually speculative, we have to wait till it becomes safe, right? So the effectiveness of prefetching drops. You can think about a simple for loop. Within that, if you are accessing your array, you are actually prefetching for that array bit late. Whenever it's in the speculative mode, even if you know the access pattern, you can't, right? Because if you do it, it's non-secure. Okay. So this is the first insight. That these are the things that are already there in my cache hierarchy, but because of the secure cache hierarchy, there is a negative interaction between prefetcher and the secure cache hierarchy. Okay. So this problem was not there if you remove prefetch request or if you remove commit request. Okay. So this problem comes only when these 2 requests go concurrently. Okay. And this is a plot just to showcase. You should look at the top half of the bar. So those are the extra traffic that is coming in because of the commit request coming from the ghost minion cache to the outer levels of cache to ensure that now the cache hierarchy stores non-speculative data. Okay. So what we found is that most of the traffic is redundant, which means even if you don't do it, even if you don't send it, you won't affect security, you won't affect any other safety issues, but it will affect the queuing delay at different levels of cache, which can actually improve my latency of prefetch request and demand request. Okay, so I won't go into the detail of all this, but we had a small microarchitecture filter which tells you whether you should communicate data from your speculative cache into outer levels of cache hierarchy or not. Okay, and the storage overhead of this filter was So this filtering has an accuracy of more than 99%, which means for 99% of the time we are able to predict whether we should populate the outer levels of cache or not, right? So the indirect way of saying it is we are able to decide whether we can reduce the traffic for all those on-commit requests. With that, what happened? We are able to improve this performance by 3.4% on a single thread. They are like single thread numbers with a storage overhead of 0.12 KB. Okay, this is actually marginal. Then we looked at the timeliness issues because your prefetcher, although it is seeing the speculative request, it can't prefetch it because if you prefetch, you will actually bring speculative data. And so this is the slide that I already showed you, right? These are more details. I think in the interest of time, I won't go into the details. What happened is these are different structures that are used by the prefetcher to predict the future access, and they are trained and triggered on speculative accesses in the past, right? Now if you do that, they are not secure. You can't do that. So what we need is a different mechanism, but please remember that our cache hierarchy is now different from a typical non-secure cache hierarchy. The data doesn't come from memory directly. It comes from the ghost minion cache whenever the instruction becomes safe, right? So all the latency calculations that we did to find out when is the best time to prefetch is going for a toss now, right? So what we instead did is we came up with a new structure which tracks all these latency calculations speculatively the structure will be squashed the moment you do a context switch, right? Even if you store all this data, this is not accessible, or you won't use this data to trigger prefetching speculatively. You will just use it to learn, and you will prefetch later when the instruction becomes saved. But the access patterns are now trained speculatively. Right? And with this, we actually guaranteed that we are able to do secure prefetching. The structures are actually safe. They won't lead to any new transient execution attacks through these new structures. Okay. Quickly, I'll go through the numbers. You should look at the right-hand side. This is a new proposal on top of what we proposed just 2 minutes ago. So it tries to bridge the gap that we had with the non-secure prefetcher, right? Okay. I think I have 2 minutes. Okay, I'll quickly go through the last attack vector, which is called the row hammer attack. It's actually not an attack to start with. It was a reliability concern which became a security concern. Okay, so your DRAMs are getting denser and denser, and this particular row hammer phenomena is actually illustrated with this following animation. So if you keep on accessing a particular DRAM row again and again, you will start seeing bit cliffs in the adjacent rows. Okay, so it started as a IISc 2014 paper as a reliability concern. It was no security angle, but then later the security community jumped into it, saying, okay, if I know this particular row is storing some other process OS pages, I can flip that bit. Page table will go for a toss. I'll be the boss for the entire system, right? Okay, so the problem at hand, it's pretty interesting problem. With the emerging DDR standards, the number of hammering that you need to cause a bit flip is actually going down. So if you look at numbers 10 years ago, you need to access a particular DRAM address 140,000 times. And now for DDR5, we don't know the numbers, but it seems like it will be few hundreds. Which means if you just keep on accessing a particular address 100 times, you'll start seeing bit flips, at least one bit flip, right? What's the solution? Okay, I'll skip it, assuming you all understand how it works. This is showing how exactly you can do row hammer. Okay. What we did is the following. The community or the industry, they actually track what are the rows which are getting hammered again and again. You track them, and the moment you see that they are crossing the row hammer threshold, the DRAM controller will actually send a refresh command, right? So remember, these are capacitor-based devices. They have a refresh interval of 64 milliseconds. So within 64 milliseconds, the attacker can try to do many activations, right? And the modern technology, what they do, they put a counter for each row, saying how many times I have actually activated, right? If I cross a row hammer threshold, I will send a refresh signal to mitigate. But if you do that, you need to store hundreds of MBs, right? Just to store the counters, right? The idea that we had in HOST, which is a premium hardware security conference, is that can we steal some of the last level cache space to store these counters and track row hammer. And eventually, when we find that some of the rows will actually cross the threshold, we'll inform the DRAM controller, go and send a refresh signal. Okay? The motivation behind this idea was this. I'll exactly take 1 more minute. This is the motivation. So if I'm a row hammer attacker, my playground is 64 milliseconds, right? Within that, I can activate many DRAM rows, but fewer number of times. Or I can activate few DRAM rows, many number of times. So as long as I can track these rows and their row count in my last level cache, then I can actually save all the storage that the modern technology is actually using. Okay? So this is what it is. We're actually reserving few LLC sets and ways to do all these things. And then finally we showed that you can do all these things with very little storage overhead. Performance numbers look really good compared to the prior works. The interesting thing about this work is this work appeared 2 months after the HPCA paper from Georgia Tech. 95% of the idea is the same. Right? If you read both the papers, almost 10 pages look same, apart from few microarchitecture tricks, right? So again, I think we are out of time. We'll just quickly go through it. So these are the series of attacks that I talked about, not from offensive security perspective, but how to design secure cache, prefetcher, how to track row efficiently. So these are not my works. These are actually works done by my students. They're like UGs or master students at IIT Bombay. So this is my group, and if you want to look at the other kind of work that we do, please go through this QR code or go to our webpage. You'll find some other papers that I didn't talk about here, right? With that, thanks. I took extra 2 minutes.
Questions?
All are waiting for tea now.
I will start. So, the point that you mentioned about the row hammer attack and a defense mechanism to refresh.
It's a row hammer tracking. It's not defense. Defense mechanism is just sending refresh signal.
Yeah, refreshing, right? That's kind of counterintuitive because if a row has been accessed recently, you don't need to do a refresh.
No, you have to do refresh for the adjacent rows.
Oh, you have to do the refresh
Yeah.
for adjacent rows. Okay.
I'm the aggressor. The
Okay,
victims are the.
Okay.
Yeah.
Because the techniques that try to save on refresh essentially use this thing, right? If the row has been accessed, you don't.
That's the
So
optimization.
I missed the point. Sorry.
Yes, yeah. Because anyway, I'm accessing myself, right? Why should I refresh? Yeah.
Hi. So for the last level caches in the recent chips, there are concepts of memory partitioning coming in.
Cache partitioning.
What would be the implications of memory partitioning on these kind of attacks?
Which attacks? First one, second one, third one?
Row hammer as well as...
Row hammer has nothing to do with cache.
Okay.
Yeah.
How about the Spectre and other?
Again, as long as there is a cache, you'll be able to do Spectre.
But if you partition it, the access to those...
It's okay as long as there is a cache, right? Which is a microarchitecture unit. You don't squash it when you do misspeculation, right? You'll be able to do Spectre.
How are you keeping track of the counter, for the right hammer in the cache?
These are simple saturating counters, right? What we do is we take the row number, index that row number into last level cache, and start storing counters for those rows. So what we do is we store those counters for group of rows, because as I said, right, you can actually access many rows few number of times, or you can access few rows many number of times, right? So you can actually have two structures. Depending on that, you can do indexing and then maintain their counters.
Okay, any more question? If there is no more question, we can have another round of applause. Thank you.
Oh, okay.
Small second of
Thank you. I will grab it soon. Because everyone is waiting for tea. Okay, thanks.
Okay, so that's the end of today's systems day, and we will now proceed for the high tea. Let's have big round of applause for all the speakers, all the audience, and the organizers. And I think the posters are still out there, so if you want to have another round of discussion, feel free to have that. Okay, we'll go for IT. And I'll put all the photos, all the presentations in the website. Okay, whenever they give the photos. Thank you.
I expected for 45 minutes. 75 minutes or, sorry, half an hour, 75 slides. Animation. Very nice. Okay. Thank you.